So we've gone to clarify.com, downloaded Molecular Maya, which is the plugin we'll be working with. We've got this mmaya install, and we've opened that in Maya and installed it. So at this point, we should have the mmaya editor here. And if you don't see it, it automatically creates an icon in this top right row of plugin editors or other editors along with the attribute editor. So we've got mmaya, which we can launch here. There's a number of modules that, well, currently in development. There's a double-stranded DNA, which is available for purchase, but we're just going to be talking about the free protein databank import and editor. So what kind of data are we going to be needing to work with? Well, that's can be found in many places, but the most prominent of which is the protein databank itself. And the rcsb.org is the URL that you can go to find the protein databank. And it has a lot of features which I'm not going to dive in too deep, but the simplest way to get PDB IDs to work with is just by searching for something. So maybe we're interested in DNA ligase or something like that. And then we get a whole bunch of entries here, which we'll talk a little bit more about in a minute or two. But sometimes they'll actually be a molecule of the month that the molecule has been featured in. And so the molecule of the month, I'm just going to jump over to the main molecule of the month. The molecule of the month is a great resource for learning more about proteins and molecules. And it's a great place to start if you're wanting to find if you're wanting just to experiment a little bit with Molecular Maya. This is a great area to sort of pick examples from. So for example, we can look at trypsin, which is a molecule that breaks down proteins. In addition to a sort of description of the molecule, the protein, how it works, nice illustrations and some more details about the function. Typically, there will be identifiers that are actually within this text that will give you protein databank entries that you can work with. So, for example, here, this we can see that trypsin here, the one at the top, is from entry 2PTN. And so if we click on that, we can see this entry here that is giving us trypsin. So in order to get something into Molecular Maya, this 4-letter identifier is the one that we want to be concerned with. So I'm going to copy this, or just memorize it to PTN, and jump back to Molecular Maya. So the active module here, Pdb Import, this is the one that we're going to be talking about. So if we click on that one, we get this sidebar here that has a few different tabs in it. One of them is just a regular import tab, and this is for importing stuff that you've already downloaded. So you can left click here in this, and you can see that by default you've got a few different proteins downloaded, PDBs downloaded into a local folder, and you can click on the folder and see where those actually are sitting in your preferences folder. You can search elsewhere on your hard drive if you want to. But we haven't downloaded the protein yet, so what we want to do is jump over to this download tab, and we'll paste our identifier in here to PDN for trypsin. And the source for now, the PDB is the only source that we have available to us. And what we want to do is we want to check the import post-download. So once it's downloaded to our source path here, we also want to import it into the scene. So we'll click download, and it's going to go to the protein databank, fetch the data, and bring this molecule into our scene. Great. So what have we actually created in our scene? Well, we've got, whoops, pressing the wrong keys here. We've got this CPK atom display by default here, and we'll talk about different representations in a minute, but I want to just take a look at the outliner and see what's been imported. Well, in this course we haven't talked about N particles, but what's being presented here are actually N particles, and N particles and any N dynamics require a nucleus solver, and so that's this solver here that's hidden actually, and basically you don't want to touch that. That's just the engine behind the scenes that's helping build all of this stuff. So don't touch the engine. And then we also have a group that has this special structure node here, and then underneath we have model 1, which is our protein and chain A. And as we'll see a little bit later, other proteins have multiple chains that we can work with independently, but trypsin just has one chain. And there's a little box icon beside it. That means that this node has been black boxed, which means that you can't get inside it, and and the details of it are hidden from you. And that's in most cases for your benefit, so you don't accidentally mess things up that are going to break the function of this process. But for my own purposes, I've found that sometimes I do want to get in there, and I've made a little script that will actually unbox that and kind of get access to the inner workings. Basically, my understanding is later on in the development they'll give access to things that people might want to do. So in the outliner there's a few things, and they refer to the chains that your different proteins have, but you don't really want to change anything. You definitely don't want to change the hierarchy in here or change things or even rename them here. If you do want to rename your molecule, this top bar in the molecular Maya, you can click on the pencil icon and you can click rename, and we can call this 2-PTN trypsin. Click rename. And apparently I had some invalid characters. Oh, I see. Nodes in Maya cannot start with a number, so it's important that if I wanted to call it 2-PTN, that I have something in front of that. So we'll call that PDB 2-PTN trypsin or something like that. This is also where we could delete the protein or the molecule. It doesn't really work. I don't think it works just to hit this and hit delete. You're going to say that it has locked or read-only children, and again, that's to do with this black boxing. So if you want to get rid of things in your scene, you actually need to use this pencil icon again and hit delete. So I'm gonna re-import this by clicking on the Import tab, going to find my 2-PTN, and there we got it back. I could rename it again, but I'm not going to in this case. So underneath this main header where we had this rename and delete, we also have an appearance tab and a PDB details tab. So this PDB details gets descriptions from those files, and these are very helpful, especially if you have a much more complex molecule, which we'll look at, to understand how the protein is constructed. So in this case, we just have this chain A, and if we look, chain A is trypsin. Okay, so that's good. We got what we wanted. And you also have a link to the PDB entry, which is a handy little link. This trypsin molecule, again, we might want to view it in different representations. So the first one, again, that comes in by default is an atomic representation with a CPK model, and there's various options that probably you don't want to change too much. But there's another representation that might be useful, ball and stick. And so ball and stick is something that you might be more familiar with building models in chemistry class. So the atoms are represented as spheres, and the bonds are represented as lines between them. If we select the protein again, we have some options. So the bonds are represented as lines in the viewport, but when we render them, they'll be rendered as cylinders, as actual geometry. But if we wanted to see the geo in the viewport, we could click geo, and you can see that it slows down the scene a little bit, but you can actually see the radius of the bonds here and how they're represented. There's a few presets that you can play with, like a pinch model and pulse bonds. I'm not really sure the utility of these things. I'm not a chemist, so but there's different things that you can play with. The only tricky thing about the ball and stick model is there's a bit of a bug that may or may not be fixed in the near future. Okay, so if you're on the ball and stick representation and you turn off the atom viz, and you've got the the bonds as lines or geo, those will stick around. And so the way to hide those is to return to a CPK model and then turn the atom viz off. So if you find that you're in ball and stick and those lines are sticking around, just switch back to something else and hide it. Okay, so that's a couple different atomic representations. We also have a surface representation, and so if we click on this mesh viz, we can visualize a mesh for this protein. And the default settings are pretty low and blobby and large. There's some presets here. We can bump that up to medium, which is a little bit more refined, and we can even come up to high. And with a high representation, it takes a little bit to generate. There's a lot of polygons here, but this is more, you can see kind of almost the individual atoms that are making up this protein, and it adheres much more closely to the surface. In several instances, this mesh is what you're going to be wanting to use if you're going to be actually animating a molecule and in your 3D scene. Although by far it's not the only representation that's useful. Let's take a look at backbone. Okay, so if we turn on the backbone, what we're going to actually get is a NURBS extrusion of the backbone of the polypeptide chain. So this isn't representing any side chains, it's just representing the backbone of the peptide. And we can turn on caps, which are going to create little spheres on the end of the surface, kind of round it out. And if we click on wire trace, that's actually going to create a CV curve inside it that, again, we can't really extract natively, but if we wanted to do something with this wire, maybe create our own backbone representation or use it as a rig to animate a molecule, there are ways that you could extract it to get access to that CV curve. If you wanted to extract this, probably the simplest way is just to hit Command D and then Shift P. So what Command D, obviously, it duplicates the selection, and then Shift P is it unparents it from the depths of this process. And if we can see we have this new node or new group in the outliner, and now we actually have access to these individual nodes. For example, this backbone wire here, if I pull it out, you can see that this is a CV curve that follows the backbone along. So that's one way to get stuff out of it. But it's important to note that this stuff here is now been severed from Molecular Maya. So if you're wanting to change the properties of it, you're going to have to sort of delete this and redo it here. So you've broken that connection to Molecular Maya. Okay, so there's also this secondary structure cartoon representation that I'm just going to hide these ones and click on that one. And what that's going to build, if it takes a few seconds, it's going to build a representation that takes into account some of the secondary structures of proteins. So things like alpha helices, which we can see here and over here, as well as beta chains, beta sheets, where you can see this this flat ribbon is representing one strand of the beta chain or beta sheet here and then here, so that's anti-parallel, and then there, so that arrow's there, and then that one there, and that one there. So this gives you some more information about secondary structures and motifs that are present in this protein, which might be useful for a certain kind of project. Unfortunately, at this point, there doesn't seem to be a way to hide this secondary structure cartoon in contrast to these other representations. So unfortunately, we can't delete it. So hopefully there'll be a way to kind of toggle that in the near future. So biological unit is not relevant for trypsin because trypsin exists just as a monomer. But if you had a protein that was a homodimer, or if there was like even things like viral capsids, if there was a situation where your protein was part of a larger complex where you had transformations for repeating units, then the PDB database might have some information about how those transformations occur. We can jump back to the PDB and just look for a viral capsid. This is always kind of fun to do. We won't choose HIV capsid because that's a lot more complicated, but maybe parvovirus. This looks cool. It looks quite large though. But 1FPV, so let's download this 1FPV. Okay, and if we turn on Mesh Viz, and I'm just going to do a medium setting, and I'm going to turn off the atom representation, so I just have the mesh, or just the surface representation. So you can see that this doesn't match what this illustration is showing. And that's because we only have just one subunit of the larger capsid. But hopefully, if we click this button here, download from the PDB, then this is going to download the information required to build out that larger complex. And now if we check meshes, and this might take a little bit, not too long, we actually get the full protein capsid. And what's going on here is, you can see, is actually instancing that mesh, because you can see I've just selected a few vertices here, and the same vertices are selected over the whole mesh. So this is actually an instancing operation. So now we've got the full capsid built up of that single monomer. And if I select the PDB again and come back to the Appearance tab, there's the option, if I uncheck that, it's just going to hide the meshes, which means that bringing them back is very fast. Or I could say that toggling this off deletes the units, in which case bringing this back is going to require rebuilding it again. So a couple options for handling those biological units. The last couple of tabs, B factor is about thermal jiggle with atoms, and so I'm not going to talk about that. It's kind of a fringe case, which you probably won't run into the need to worry about too much. And there's also a morph, which requires that you actually have PDB data that exists in multiple states, and you can morph between them using the Yale Morph server. So if we come back to the Create tab up here and click on Morph, the Yale has a system where you can choose two PDBs that represent the same structure with the same atoms in them, and this server is going to generate a series of PDBs in between them that are going to transform from one to the other. And so if you have that data, then you can bring that into this system and you can create a morphing animation between them. But again, that's less, you're less likely to run into that, although you can read up on that if you're interested in doing those sort of morphs. Many PDBs don't have that data associated with them, or multiple states that have been solved, so it's less common that you'll actually have that data available. If it's in a PDB format, you can. So for example, I was able to find, I probably won't be able to find it now, but there was part of a lipid membrane that had been solved as a PDB structure. So when I imported that, it worked, but it didn't have, so PDBs often have a lot of information in the header about what different chains represent and various details like that. And so if you import your own PDB data, if you're able to find it somewhere, it may just import it just as a single block that you can't really do too much with. You can't mesh it with individual chains and stuff like that. So you might be limited to your functionality, but it's worth a try if you can get the PDB data somewhere. It's a text format. I mean, we can take a look at it. Okay, so the PDB file format is just a text file, and what it has is several columns. There's an atom, what it is. There's an atom. This is atom number 54. It's a carbon. It's part of amino acid alanine, and here's the coordinates. So it's a very simple file format. You wouldn't want to create it by hand, but it's a pretty common file format for molecular structure. Basically, you just need the atomic coordinates in a flat file, and it should be able to read that. So, and all of this header information is useful, but not required. Okay, so let's look at a little bit more of a complex, sophisticated case, which is going to highlight some of the pitfalls and other aspects of working through the protein data bank. So let's say I have something specific in mind. I want to use a protein structure, maybe ATP synthase. So I'll search for ATP synthase, and we do get a molecule of the month feature, which is good, but we also get a lot of results. So we've ended up with 434 results here. So it's not advisable just to pick one blindly and download it and use it and say, yes, that's ATP synthase, because there's a few things we need to worry about. The first one potentially being, what species is this molecule from? So this first one here, you can see it's bovine, so this is from a cow. The next one is from yeast. So these are very different organisms, and depending on the molecule and depending on the purpose of it, and depending on how far apart these species are in relation to each other, you might have a very, very different structure. For example, if you have a ribosome from a prokaryote versus a ribosome from a eukaryote, it would not be appropriate to use those interchangeably. So in this, we've got something from a bacterium, and we've got something else from a cow. So the first thing you want to know is, do I need to use something from a human? Does it have to be from a human? Is another mammal close enough? And in many cases, probably most cases, protein from a mouse or a cow and a protein from a human are going to be pretty much indistinguishable from one another, unless you're an incredibly specialized, knowledgeable individual. So whereas something from a bacterium maybe less so. So that's something to be aware of. The other thing that you kind of want to look at here is whether, for example, there are other things that are in complex with the protein that are going to be downloaded and imported in addition. So for example, here we've got bovine F1 ATPase covalently inhibited with this chemical. Is that chemical relevant? Is that going to be something weird in your scene? I'm not too sure. So here we've got complexed with an inhibitor protein. Okay, well, is that inhibitor protein? Should that come along with it, or should we find something that doesn't have an inhibitor protein associated with it? These are things that you might want to look into. The other thing that you want to be aware of, and this is probably the most relevant question, is how much of the protein are you actually getting? So for example here, so we've got alpha-3 beta-3 subcomplex of F1 ATPase. What does that mean? Well, so my guess here with my limited knowledge of the ATPase complex is that there are 3 alpha subunits, 3 beta subunits, but that's not the entire thing, right? So we've got a solution structure from subunit F6 from the peripheral stalk region of ATP synthesis. And that's a tiny little component of it. So it's not always obvious whether or not you have all of the information there, but it's definitely critical that you actually try to investigate that. So we've got F1 ATPase. So is that the entirety of ATP synthase? Well, again, the molecule of the month is a pretty good place to start. So let's take a little bit of a closer look here. Okay, so this ATP synthase is a large complex, and it's made up of many chains. We've got the F1 region, we've got the acyl here, and we've got the F0 region, F0, I suppose. And this is embedded in the membrane. And we also have this stator thing, and it appears as though at the time of writing of this article, which was in 2005, albeit that's a long time ago, they didn't actually have part of the structure solved. So do we have that information now, or is that information still missing? These are things that you need to find out. And typically, the newer structures are A, more complete, B, better resolved at a higher resolution, and potentially C, with more species available. So even though it might be simple to just click on one of these IDs and get the A1C12 subcomplex of this was deposited in 1999, and there probably is a bigger, better, more complete data set to work with. So do a little bit more investigation. Maybe we want something that's going to be representative of a mammal. So we could try Homo sapiens, but I did a little searching, and if we look for Bos taurus, which is a cool Latin name for this cow, and we get bovine mitochondrial ATP synthase, state 1A. Oh, So we've got state 1b, state 2a. Well, what's all this about? Well, it turns out that all of these structures have been solved with and are presented in the same article. So the citation is also important to look at. We've got the structure and conformational states of the bovine mitochondrial HPC synthase by cryo-EM. Well, that's pretty cool, actually. So what this is actually depicting is different conformational states of the same molecule. So this might be an instance where you could go to the Yale Morph server, plug in these different states, and actually have a full animation of this molecular machine at work. So we're not going to do that. We're just going to be looking at a single state, but like state 1a is going to be sufficient for us. So what does this actually have in it? There's far too much information here to actually get into. So the literature is definitely a great place to start if you want to understand more about the molecule, and specifically the entry in the database and what it actually pertains to. So you can look up the citation. You can also see different structures, different PDB entries from the same citation. So for example, if you had a large protein complex that the authors subdivided into different PDB entries, you might find one here and say, this is component A, but then you might also say, okay, here's component A, component B, component C, component D, and you've got it all sort of together as one. And so that's a great place to look for those related structures. In this instance, as we saw before, this is not corresponding to different components of the structure, but to different conformational states, 1A, 1B, etc. We can read the abstract to get a little bit more insight into actually what this structure is related to. It could be that it turns out this is ATP synthase with some kind of genetic modification or deletion, so that the authors were investigating some property of it, which may not be appropriate to include in your animation because it's a mutated state of the protein. So we can look at that. We can also check out where the affiliation. Oh, Sick Kids, Toronto. Well, that's pretty cool. Who'd have thunk? Okay, so then we scroll down a little bit more, and we start looking at the actual components of this molecule. And we want to click Show All Chains so that we can make sure that we see everything that's here. And if we scroll down, we also want to make sure to click Show All 11 Protein Entities so that we're seeing the chain identifiers on all of them, as well as all of the chains that are actually in the molecule. And this information, for the most part, will also be available to us within Molecular Maya, but it's good to read up on it before you spend the time importing it so that you know what you're getting. At this point, we might not know very much about ATP synthase yet, although we hopefully will have done a little bit of reading. We can see here we've got subunit alpha, and this is chains A, B, and C. So does that mean that there are 3 chains that make up this individual subunit? Okay, we've got subunit beta, D, E, F. One place, well, there's a few places here. Uniprot is another database of proteins that is not about structural data as much as it is about functional data, features of the protein. Like it's a massive repository for all this information. And so if you really want to get a detailed understanding of what that protein is about, the Uniprot can be. There might be some aspects of here that are helpful in understanding the protein. The other thing that I wanted to point you to was this full protein feature view. So for this particular protein, and specifically this subunit structure, I found helpful. So in this, the function is also helpful to read up on if you don't know what your protein does, but the subunit structure here. So we've got 2 components, CF1, the catalytic core, and CF0, the membrane proton channel. So we already saw that in the molecule of the month, so that's good. Okay, CF1 has 5 units, alpha, of which there are 3, beta, of which there are 3, gamma, delta, and epsilon. Okay, well that's very useful to know. CF0 has 3 main subunits, A, B, and C. Okay, that's also helpful to know. So, and it has some other information about the interactions. So that gives us a little bit more information to work on. So we've got the 3 alpha subunits, that's good. 3 beta subunits, that's good. We've got gamma, delta, epsilon, that's good. So it appears that the F1 component, all of this is complete in this structure. Is that all that it has? Well, it has more. Okay, so we've got F0 complex subunit, and we've got 1, 2, 3, 4, 5, 6, 7, 8 different copies of that. Well, that probably corresponds to each of these. 1, 2, 3, 4, 5, 6, 7, 8. Hopefully that's the whole rotor. ATP synthase subunit O. What's subunit O? I'm not really sure. Okay, so now we're getting into things where it's like, I'm not really sure exactly what these things are for. So there might be a little bit more putting puzzle pieces together and trying to understand what's going on. But I think we have enough information to assume that we've got a pretty full representation of the entire ATP synthase structure. So let's download this 5ARA. So because this is a larger structure, this takes a little bit more time to import. So you might see a spinning beach ball. That's totally okay. Give it a little bit of time. Okay, so now again we've got this imported as a protein structure. Well, this looks pretty cool. This looks pretty much exactly like the molecule of the month, including some of these extra components. So hopefully we have pretty much the whole structure here. One thing I haven't talked about is actually manipulating the transforms of this protein. Typically what we want to do is we want to select this PDB mol struct group, get the move manipulator, and if we want to center it on the grid, we can hold down X and middle mouse click there on the grid, and then we'll snap that right to the grid. And maybe we want this to be oriented like we saw in the molecule of the month, so we can get the rotate tool and rotate that up. Oops, a little too far. Okay, so now we can see this a little oriented and positioned a little bit more normally. And if we jump over to the Appearance tab, now we can actually see individual chains, and we can actually manipulate these chains individually. The PDB Details tab is going to be helpful for us because here we can also see, instead of jumping back to the PDB site, we can also see, okay, so chain D, E, and F are going to be the subunit beta. So let's maybe select D, E, and F and do a mesh on those. Okay, so that you can see those are the beta subunits. We could choose A, B, and C, which are the alpha subunits, mesh those. And so you can see that we can do this all in one shot for sure, but it's kind of neat to sort of build this up and see what the components are actually corresponding to. Yeah, I'll just do them all at once. Okay, so we've got a mesh representation, and maybe we want to bump that up to a medium, or we could put in our own custom parameters. So what I recommend for putting in custom parameters is to enable this update on demand, so it doesn't remesh every time you change something. So I'm going to change the resolution to something like 4, which is the smaller the number, the tighter the resolution, or I guess the higher the resolution. And I can bump up the smooths to something like 30. I don't know, just smooth it out a little bit, and I'll hit update. There we go. So that's a little bit nicer. So you can see we've got all 8 subunits in the rotor up here. We've got some of these linker stator components, and we've got the F1 subunit or complex down here. If you wanted to get this mesh out to actually work with, I talked about just duplicating the whole thing. Another way that's built in here, and this is probably a better way to do it, is to actually extract. If you just want the meshes here, you can choose this button, and this is in the surface tab, so where we were modifying the properties of the surface. We've got extract selected chain meshes. So with all of the chains selected, I'm going to hit extract, and now we get a new group out here outside of the PDB sort of black box structure with individual meshes. And so that's a good way to actually then go on to the next part of your pipeline and work with the meshes. So maybe we would want to kind of add new materials to each of these objects. We can hide the original one, just hit H, and that's going to hide it. But maybe all of these, let's just assign the existing material. You can see that the Maya or molecular Maya creates a lot of different materials for each chain on your molecule. We'll jump into the hypershade, and we'll just assign Lambert 1. And so you can see we've got the base mesh. You can see here on the on this particular mesh, and this happens from time to time, there's a bit of an error here in the meshing. And that's just because the mesh is generated based on the tolerance between particles, essentially, and sometimes there are mistakes. So you can definitely retopologize these meshes, whether this is using the quad draw tool that we looked at before. Jump back to the quad draw tool. You know, putting down faces and stuff like that. But that's time consuming, and it isn't too necessary in most instances, but that is a possibility. There are automatic retopology things in things like ZBrush, but maybe this mesh is okay. You just want to help fix this issue. So we can go into Vertex Mode and select these two vertices. Might be a little tricky to zoom in here, and maybe the simplest way to fix this would just be to do an average vertices. And so we can just bring those in and kind of smooth it out that way. Now this might already be fixed, and I hope that it is, but I have had in the past an issue where the mesh has been essentially locked, and the way to fix that is just to go into the mesh controls in the shape node and make sure that allow topology modification is checked. And then you can do what you like with the model. So that's just a overview of some of the main molecular Maya features and workflows that you probably will run into.